not too far from where I live is this really long straight road in the country, and in it there's a small bump over a railroad track, but it drops a lot on the other side. And you have to be careful not to drive too fast because it takes you unawares and you end up getting liftoff. Okay? Now if we assume that that road has a circular curvature to it over the railroad track, I like to ask the question, what is my maximum speed I could go? Not like I try, I'm a good law-abiding citizen here. But what would be the maximum speed I could drive to not jump the hill, but to remain in contact the whole time? Okay, so that question, we need to get quantitative with that condition. What condition am I looking for? Where am I actually, like a numeric value or a variable, what am I looking for to say how fast I can go so as I don't jump the hill? And so to think about it, let's go ahead and draw a free body diagram. Let's assume at the top of the hill, the car's sitting there at the top of the hill, and if it's going too fast, it's going to jump, and if it's going slow enough, it'll stay in contact. So let's look at this and draw a free body diagram. What do I see? Okay, so at the top, here's my car. Here's my free body diagram for the car, and I see a normal force holding it up, and I see gravitational force down. Okay, there's likely a frictional force, rolling friction. Let me get some labels here. Normal force, force of gravity, and a propulsion force, especially if I'm moving at constant speed. My propulsion force ought to be equal to this rolling frictional force. Okay, so I've got those four forces drawn here. My question is, I don't want to jump. What does that mean? Okay, now if I say it the other way, is I want to remain in contact with the road. That kind of points our attention to this normal force. What is a normal force? Well, it's a contact force, the road holding us up. And if I go too fast, that means I'm going to leave contact from the road. Okay? And there would be no normal force because no contact. Another way of saying it is, if I do jump the hill, then I must be in free fall, or the only downward force, in fact the only force at all, would be the force of gravity, which again points to saying that the normal force disappears. Okay? So by looking at this, our condition really is saying that the normal force goes to zero. Now think about that progressively. Let's suppose I'm driving super slow, really slow on this road. Okay? Well, that means when I'm at this point, I'm pretty much stationary. My normal force is going to be equal to my gravitational force. But if I go faster, then I'm starting to get this centripetal motion, this centripetal acceleration must be getting bigger because of that tangential speed. So to make that clear, let's take this and now translate it into Newton's second law. So at that point, my radial acceleration is straight down, so that would be a y component. So my F net must be down since I'm going over this curve, and my acceleration radial is down. So if I look in that radial direction, I choose down to be the radial direction. Okay, so look in the radial direction, I have F net R equals MAR, which equals mv squared, that's the tangential speed, over the radius of the curve of the road. Okay. Now what is it? So that's taking care of this side. What about this side? Well, downward I've chosen to be positive, so I have mg minus this upward normal force equals mv t squared over r. Okay, so if I'm going super slow, like really slow, then this term gets closer and closer to zero, and I see that my normal force is pretty much equal to my gravitational force. But if I start going faster and faster and faster, okay, then the only thing that can change here is the normal force. The gravitational force is a product of g and m. Those don't change no matter how fast I'm going. And so that means if mg minus n gets to be a larger number than 0, the only thing that can happen is if n is smaller, I'm subtracting less from mg. It also means the biggest this can ever get is mg. And that is our condition for free fall, our acceleration summing between g. Okay? So our n approaches 0 when our tangential velocity approaches this maximum or critical speed to get around that curve without jumping. And so in doing that, we end up with mg equals mvt squared over r. The masses cancel, so it doesn't matter if I'm in a bus or in a Cooper Mini. Okay, and I find vt equals the square root of rg. Okay, now we've seen that form before, and here again it comes into play. That this critical speed, this is v critical, right? This critical speed is when only gravity is acting. The only force acting on you in the radial direction is gravity. Okay? And so this is that critical speed. So if I go any faster than this, I'm going to lose contact with the road. If I go exactly at this speed, I'm just going to barely lose contact with the road right at the top, and then I'd regain contact just barely afterwards. Okay, so that is an example of thinking carefully about circular motion and gravity, particularly circular motion in a vertical plane, or where the radial direction points downward towards the center of the Earth.